Hey friends, Dr. Boroli here. Welcome back. We will go to part 2 of the section on BJT. In the last portion, we have seen common base configuration. Now let us see very important common emitter configuration. Here in first figure, the NPN transistor biasing is shown in common emitter configuration. See, base to emitter junction is forward biased by the supply voltage VBB, that is base circuit supply. Whereas collector to base junction is reverse biased by the collector circuit supply VCC. Since emitter is common between this input circuit and output collector circuit, that's why the configuration is called common emitter configuration. Here, IB denotes the base current, that is input current for the configuration. VBE denotes base to emitter voltage in the input circuit, whereas IC indicates the collector current in the output circuit and VCE is the output voltage. So therefore, zero signal value or quiescent point value of VCEQ and ICQ are established by supplying the value of IBQ and VBEQ in the base circuit, that is called as biasing. Since emitter is common between input and output circuit, this biasing is called as common emitter circuit configuration biasing. Figure 2 here indicates the biasing of PNP transistor. The only difference is VBB and VCC power supply polarities are reverse. Since PNP device will be properly biased base to emitter junction in forward bias by using negative power supply VBB, and collector to base junction reverse bias can be obtained by a negative supply VCC. The direction of the currents are also opposite to that NPN transistor. The current gain in C configuration, it is denoted by the letter beta or the symbol beta DC, and it is defined as the ratio of output current to input current. The output current is IC and the input current is IB. Since IC is much higher than IB, we have seen from the operation of the BJT. Therefore, the ratio IC by IB, that is beta, is always much greater than 1. For common base configuration, we have seen the current gain is alpha or alpha DC. Let us find out the relationship between the current gain alpha DC and beta DC of common emitter configuration. Let us see the equation. IE is equal to IC plus IB, that we know. But IC is nothing but beta into IB, because IC by IB is equal to beta, just defined in the above equation. Substituting this and taking IB common. So IE becomes 1 plus beta DC into IB. Whereas we know alpha DC is equal to IC by IE. Let us substitute the value of IE here. We know that the current gain alpha DC in common base configuration is the ratio of IC by IE. So just substitute the value of IE from the above equation. It becomes IC upon 1 plus beta DC in bracket and into IB. IC by IB is identified as beta DC, and therefore alpha DC is equal to beta DC upon 1 plus beta DC. From this equation also, since beta DC is much higher than 1 can be ignored, and therefore this figures is approaching towards 1. Similarly, beta DC is equal to IC by IB. We have just defined. But IB is nothing but IE minus IC. Substitute the value of IE and take IE common. Taking IE common from this equation, IE into bracket 1 upon IC upon IE. So in bracket, the ratio IC by IE is nothing but alpha DC. And therefore, denominator becomes 1 plus alpha DC. And here we will identify IC by IE as a ratio, that is alpha DC. So therefore, beta DC is equal to alpha DC upon 1 minus alpha DC. For alpha DC of 0.99, because since the alpha DC is approaching towards 1, it's very close to 1, beta DC comes out to be 0.99 divided by 1 minus 0.99, around 99. And this indicates that beta is always greater than alpha and much greater. The collector current in IC configuration. Let us revisit. IC is equal to beta into IB, we know. Here we consider the leakage current component due to minority charge carriers generated due to thermal agitation or atmospheric temperature, and therefore IC becomes beta into IB plus ICEO. ICEO stands for collector to emitter reverse leakage current with base open. It is also called as reverse saturation current from collector to emitter. The reverse saturation current ICEO is flowing from collector to emitter when base is open, and it is defined as ICEO equal to 1 plus beta DC into ICBO. ICBO is the value of collector to base current when emitter is open. So therefore, ICEO comes out to be, when base current IB is 0, it becomes 1 plus beta DC into ICBO. This ICEO is much higher than the reverse leakage current of the collector junction in common base configuration. ICEO is the reverse leakage current in common emitter configuration. So we can conclude that the reverse leakage current in common emitter configuration is much higher, or 1 plus beta times higher than the reverse leakage current generated due to temperature in collector junction area, that is ICBO, in common base configuration. One characteristic of ICEO is it doubles for every 10-degree rise in temperature. Now let us study the input characteristic of BJT in CE configuration. The following figure shows the input characteristic. Input characteristic is defined as, or it is called as VI characteristic, input VI characteristic. It is the relationship of input current versus input voltage. In common emitter configuration, the input voltage is VBE as shown in figure and input current is IB. Therefore, input characteristics are VB versus IB as shown in the following figure. You will see on x-axis there is VBE and on y-axis there is IB. IB is very small, therefore the unit shown on y-axis is in microampere. We see these characteristics, those are similar to a PN junction diode which is in forward bias, because base to emitter junction is, by the way, a forward bias PN junction diode, and therefore input characteristics are nothing but a PN junction characteristics of base to emitter junction. From the characteristic, we can see the slope of this characteristic in the active region. Below 0.5 volt, we say that the device is in cutoff, and above 0.5 volt, the base to emitter junction is moving in forward bias, and that is to in forward active region. Whereas at the voltage more than 0.8 volt, it is fully in saturation state. So if you see the slope of these lines in the linear region is given by Ri is equal to delta VBE by delta IB at constant VCE. So we can take constant VCE here on x-axis at this, and we will find out the delta IB. Small change in VBE here gives rise to large change in IB. And therefore, the value of dynamic input resistance, which is nothing but the slope of the line in the active region or linear region of the characteristics, is very small. The output characteristic of BJT in C configuration are shown here. The output characteristics are nothing but the IV relationship between collector current IC versus collector to emitter voltage at various values of base current. So we have plot the various readings taken for different values of IB by increasing the value of VC and noting down the value of IC in XY graph, and that results in the graph shown here, that is called as output characteristic of BJT. What we will observe here, as IB increases, the value of corresponding value of IC is increasing, shown by the dotted line projection on y-axis. The region here below the curve IB less than 0 is called as, that is very close and touching to the x-axis from 0 to high value, this shaded portion here, where IB 0 means IC is 0. Actually, IC is just a reverse leakage current, ICEO. So, device remains in cutoff, and therefore this region is called as cutoff region. Whereas the region near y-axis shown here, where the device is fully in on state, VC will be very small during this region and collector current is large, and therefore device is fully in on state or in saturation. Therefore, this region is called as saturation region. Whereas the region in which IC is proportional to value of IB, here shown by this area, is called as forward active region. So there are three regions shown on the characteristic cutoff region, saturation region and forward active region. This forward active region is also called as linear region for BJT. In cutoff region, the device is off. In saturation region, the device is fully on and it acts as a switching device. Whereas in linear region, the collector current is proportional to the base current, input current, and therefore the device provides the collector current which is proportional to IB. And therefore, there is a linear relationship exists between IC and IB, that is constant, and we denote it as a current gain beta. And therefore, this region is also called as linear region. In active region, we have seen BJT can be act as amplifier. Whereas in cutoff region, since IB is 0, it gives to IC equal to approximately the reverse leakage current. Since beta into IB is 0, the current remains IC is equal to beta into IB plus ICO is equal to ICEO only. That is due to the thermally generated charge carriers. In active region, BJT acts as amplifier. Base to emitter junction is normally forward bias and collector to base junction is in reverse bias. IC is proportional to IB since IC is approximately equal to beta into IB. Here we have ignored ICEO. As IB is constant, therefore IC is constant in the active region. There is one effect exists in this operation, that is called early effect. When VC value is increasing, the value of IC is increasing. See here, if you see the characteristic, if VC is increasing from low value to high value, the collector current is not constant. Even though IB is constant here, for example 20 microampere, the collector current is changing from this point to this point, and therefore there is a gradual slope to the output characteristic. That is because this effect is called as early effect. In saturation region, the BJT is fully on and both the junctions are in forward bias. See here in the figure in saturation region, both the junctions, base to emitter junction, the voltage drop is 0.7 volt in forward direction, as well as base to collector junction also the voltage drop is more than 0.5 volt, and therefore it is also in forward direction. Therefore VC will be 0.7 minus 0.5, it is around 0.2 volt, and therefore VC is equal to VC sat in the range of 0.1 to 0.3 volt and IC equal to IC sat in saturation region. Since the voltage across the device is very small and current through the device is very large, it is analogous to a on switch, and therefore in saturation region BJT behaves as on switch. Maximum VC and avalanche breakdown. If VC exceeds the value of VCE max, the collector to base junction goes in reverse breakdown region, because collector to base junction is a PN junction, and since in active region we are applying the reverse voltage. When this reverse voltage is higher, the avalanche breakdown occurs similar to the avalanche breakdown in PN junctions, and that is damaging to BJT, and therefore the operating value of VC should be always less than VC max rating of the device under or BJT under use. Various features of CE configurations are listed in the table here, what we have studied. Let us go through it. Common terminal in this configuration is emitter. Input current is base current, output current is collector current, input voltage is base to emitter voltage, output voltage is collector to emitter voltage, current gain is beta DC, which is very high, voltage gain is medium, input resistance is moderate, output resistance is high, and the application, it can be used as amplifier or it can be used as audio amplifier or video amplifier also. That's all, friend, about the common emitter configuration. In the next part of this lecture, we will see the common collector configuration.